Hello, welcome back from the break. Let's see if we can continue now. So it looks that I was inactive for a while, so I might need to start new desk again. I close this tab, so I will start to restart it now. This might take a second again. Okay, there we are. So I can start NeuroDesk, and there we go. And it might remember my previous setup. Here we have a kind of little screenshot. I'm not sure if all the windows will still be open. The windows will not be open, but we still have a lot of stuff from our first session. So what I'm going to do is now delete all of this. I drag and drop with my mouse over all the things that we did so far and delete it, because we're going to do something new now. So I move this to trash. If you want, you can always also download this. For example, if you go back to the Jupyter lab, you see that there is kind of the files tree here. If you go into desktop, now it's empty because I deleted everything, but you can download the data from here. There are also options to download it directly from here, or drag and drop it even to NeuroDesk and get it back with Command Shift, I think. Before I now go into the data that we're going to look at in the second session, I would first like to give you a very brief introduction what the aim is of the second session. So we are going to generate a high-resolution activation map, and we're going to do that to convince ourselves that there is signal in our sulcus of interest, for example. So if you just run a conventional GLM, you might get noisy data that look like that, where you're not really sure, okay, here seems to be something going on. Is there something here? It looks more than kind of in white matter, but there's also a lot of false positives, or here there's definitely a cluster. This looks real. Is it really real? Or could those spots over here actually be real? So in order to convince ourselves that we actually do have a signal, very often we do some sort of noise cleaning. And there are many noise cleaning ways out there. Almost every lab has their own. I would like to go through the kind of cleanup tools out there that are most commonly used, I think, in those years, which will be Nordic or layer-specific smoothing, which both of which we have heard about, and then also clustering, which is not very different from conventional fMRI. But there are definitely other filters too, like there are wavelet filters, or there are diffusion filters, or basically masking the brain and then having a different statistic of false discovery rates, or IC80 denoising. So basically I want to show you how we get from images like that, from the same data, to images like that, where then it turns out that actually those clusters here were more coincidental. They don't really seem to survive these kind of filters. Whereas, however, other clusters, they were just barely visible, are actually real in the 3D structure there. But of course, every filter is based on assumptions, and those assumptions might be violated. So there's always kind of a trade-off. Do you really want to do this or not? Sometimes we're just desperate enough to do it. And here are maybe some reasons why we shouldn't filter our data. As soon as we do anything with our data, reviewers will make our life harder. They will definitely want to see the data with and without the filter applied. And then a filter is based on assumptions, so there might be a lot of things that might be uninterpretable after applying this filter. Very often we don't care about those aspects that are uninterpretable, but rather want to see if there's signal at all. Also, applying a filter is always just more work. You need to do it, you need to tweak it and apply it to your data. You need to compare it with your unfiltered data, validate that it's doing the right thing, so it's always cumbersome. So in an ideal world, we wouldn't really do it, right? In an ideal world, we wouldn't apply any of those noise cleaning hit, and in an ideal world, the data would be just good enough. If the data would be good enough to see everything we want to see, we wouldn't apply it, right? Which already tells you that we only apply it when we really need to. Why am I going to show you, however, now that how to apply those filter is because, as I said, sometimes it's just too noisy. I want to give you the feel of kind of how you can convince yourself if there is something in your data or if it's just noise. Also, very often other people apply those filter into their data, and then they show it in their slides. So I want to give you a feeling of kind of how to interpret other people's data. If they say something like layer smoothing of 0.5 millimeter, it doesn't sound so bad, but actually has a huge effect on the data itself at the end. So I want to help you increase your radar of how other people kind of cheat. And that has a bad connotation. I do this all the time, these kind of filters. So let's go in there. Again, let's grab our data. So here on the bottom right, the second symbol is our file browser. So I'm going there. Again, I'm going to my data directory in the subfolder of data for MGH layer course. And then let's look at the second folder here. Not the layerification, which we did in the first hands-on, but now the polishing. And we have a bunch of data here that we just grab to our desktop. So maybe let's look at that first. So we have a Nifty file, MATLAB file, sorry, and a number of Nifty files. And this is the collection of commands that we're going to run. The Nifty files that we do have is a fMRI time series and also a respective anatomical reference in case you want it. And then we also have a layer mask. Let's look at them real quick. And since we already learned how to use ITK snap, let's now use a different viewer. For example, let's use the FSLIs. Let's start this. It's setting up the container for it. And we'll start very soon, I believe. There we go. Okay, this is our time series. There's actually only one dimension that's really interesting, so I will remove the other dimensions. And on this part of the viewer, on the top left over here, I'm basically removing the sagittal and the coronal view. Actually, this is coronal, right? I removed the axial view, which is labeled here weirdly. I make this a bit smaller, and to give you a feel about those data, let's maybe run a movie. So you see this is a time series, and it has noise. It's high resolution fMRI, but it has one of the least noise of these 0.8 millimeter data that I'm used to. Let's look at some other data that we have here too. For example, we have slab anatomy, where again we might be interested in kind of these clusters that we saw previously in the introduction. We have a layer mask that we're going to use later for the layer-fMRI smoothing. Maybe I can make this colorful here. This is the fMRI that's now colorful. So I'm going up there to the color scale and basically taking any color scale that is often used for layer-fMRI. I think render 3 might be one. I changed the occupancy on the top left over here, so you can kind of see that it kind of matches. Everything that I'm doing here again is mostly to show you the pipeline, the logistics of applying those filters. When you apply this on your own data, you might find other ways more convenient or more accurate for that matter. So these are the kind of data that we're going to look at. I also included a Nordic denoise dataset, and this is just because in case you cannot follow the denoising later, you also have this in-between intermediate step available. So now let's look at some quality metrics. And I lost my FSL now. Where did I put it? Maximize. I have it back. And I will quickly. It's somewhere outside my screen now. So basically I will close it now and start it again. Again, I will open my my fMRI slab with FSLI GUI. And there we are. I make it a bit smaller now. So let's look at those data with some quality metrics that I usually look at when I do layer-dependent fMRI. And for that, I'm going to use the Laney program lnsq. In order to execute that, again, I need a terminal. So down there, I'm opening a terminal, and this terminal is now in my home directory. So first of all, I need to go to the directory where my data are. This would be my desktop. So I do cd, not capitalized, desktop. And with ls, I see all the files that are in that folder. Okay, so we have our layer-fMRI dataset. So let's run some quality metrics on that one. For example, you can do this with ln skew minus input and then the dataset that you want to do it. So I copy paste this in the terminal, and then it cannot see the Laney ln skew because I didn't load Laney yet. So I will do module load ln Laney. Now it should be loaded, and with my up key I can go to the last commands that I executed and do it again. So now it works, and it did all kind of quality metrics. It estimated the mean, the standard deviation, the autocorrelation, and let's just look at a few of them in practice. And those are exactly the same images that I also showed you on the lecture on Monday. Standard deviation, maybe skew, overall, and noise and mean. Maybe this is enough for the start. I will make this a bit bigger again, so I see my table here, and I put it to the right with drag and drop so I can select and unselect them. So here we have the TSNR, and if you move through this, you see down there that the TSNR is kind of okay. It's almost double digit, depending on the area. So if I move this down, I look at the standard deviation. So here in the standard deviation, I do see that it's not homogeneous, which I don't expect it to be, because there's grabber, G-factor penalty, the G-factor maps that basically have result in noise amplification in some areas more than in others. The overall structure that I see is that it's not dominated from kind of ghosts. I do see kind of the vessels, maybe the outline of the brain, so that makes sense. There's no huge issue with the sequence here. Similarly, when I look at the skew, it basically looks like random noise. It's flat, which is what I want to see, specifically inside the brain. Then the overall correlation, as I said before, is basically the correlation of the overall brain, a time series with each voxel individually. So this can represent both the functional task, but also physiological noise. I would definitely expect it in an ideal case that this is only a real true physiological signal, neural driven or vascular driven. The next one would be the noise, which again is not expected to be locally homogeneous. And then of course we also have the mean image, just as a reference now. So this is kind of the quality metrics that we might care about. Now let's look at the functional activation. And we can estimate the functional activation in AFNI with this command of 3D deconvolve. Specifically, you give it the input file, which would be the layer-fMRI, and then also we tell it how many task conditions we have and when each task condition starts. So we have blocks that's with condition 1 that start at second 12, 60, and 108. And each block is 12 seconds long. And then we write this out in a stats file. So let's do that. First, I load AFNI, module load AFNI, which should basically activate this account for me, this command for me. So I copy it and can execute it now. Paste and enter. And there you see it's doing the GLM for each individual voxel. And now we should have a file that's called stat.nifty, which is this file. I can drag and drop it into my FSL eyes. And now I don't see a lot because the windowing is just weird. So for this dataset, I would maybe truncate it from 5 to 12 maybe. Not the noise, the stats, excuse me, from 5 to 12. And I can make it colorful. For example, like that. So this is kind of the image that I showed you at the beginning. We have some kind of weird false positives. This is often just an artifact from motion. We have our kind of cluster here that we are not sure if it's true. We have something that seems to be activated here or maybe here, but it's not really clear if this is the bottom part of the sulcus or the top part of the sulcus. We want to clean this up now. Let's do that. And let's do that with Nordic. And Nordic is a denoising tool that's distributed by this GitHub from Steen Möller, and it's executed in MATLAB, which makes it a bit complicated for us because it's not trivial to get MATLAB licenses. So we will do this in online MATLAB, and I'll guide you through this now. So I open a browser, Firefox browser here, and I'm going to mathworks.com. So now this is MathWorks, which has a MathWorks Drive and also online MATLAB. But in order to access this, I need to log in. So I will log in, and I hope you have your MathWorks login credentials ready. There are a few kind of burner accounts in this classroom right now that might be usable for a few days. I will use one of them, namely Sovom. And the password. Let's see if this works. I accept. Okay, it did work. So I seem to have a trial license. I don't need that at all. What I do need is first to upload my data that I want to use in online MATLAB to MATLAB Drive, this one. So I go to this little matrix on the top here and then go to MATLAB Drive, and it will ask me for my password again. And in case you didn't let it save, I will give you a second so you can type it in again. The same password again. All right, so now we have MATLAB Drive, and we can upload 2 files that we need. So I go to this upload button, then it opens a little box where I can browse my data and upload my data. So I definitely want to upload the denoising part, the MATLAB functions for Nordic, but also the fMRI time series, that one. So I select both of them, and I select them with Control in order to select 2. So I open this and upload it. And this is not a lot of data, so it does not take very, very long. So now we have these 2 files over there, and we can now go to online MATLAB and do something with them. So again, I'm using this little matrix up there to go to MATLAB. And this brings me to my Open MATLAB online. So this takes a while and basically starts MATLAB in the browser. You can also use MATLAB directly in your desk, natively installed, but this only works if you have an actual MATLAB account with MATLAB license, and not only a trial license. So now I'm in MATLAB Drive, and it automatically detects the 2 files that I have in my MATLAB Drive folder, and I can execute MATLAB commands now. In order to do that, I'm now basically copying all the commands that Luca talked about in his lecture as being good choices to do denoising, and basically drag and drop it directly into my online MATLAB folder or terminal here. So I'm basically using Nordic. I don't have a noise volume at the end. I'm only having magnitude data. I have a relatively big kernel size that's asymmetric, slice by slice. This is my data set that I want to use. And I'm basically faking a face because I don't have a face. And I'm pressing enter, and now all those arguments are saved. So the next step is then to execute Nordic. So again, I'm drag and dropping this line right into my online MATLAB and hit enter. So now it's estimating a G-factor map, and this sometimes is just as long as MATLAB itself. It also uses a PCCA in order to estimate that. Then it started Nordic and it completed Nordic. And now we have a Nordic slab fMRI time series, and we can download that one. For example, here with right click on the slab, I can download it. So this is downloaded now, and I can actually open my folder, I think. This should be my download folder now. Maybe I go to the download folder directly via my file browser, which I still have it open here. There is my Nordic file now. I want to see what this did now to my data, so I'm basically grabbing the FSLI's viewer again and dragging and dropping that into my viewer in order to basically go through the time series and see how much it changed. Before I do that, I first want to make sure that I'm having the same windowing here. So for the slab fMRI, I'm using anything between 0 and let's say 30,000. Same for the MATLAB Nordic, between 0 and 30,000. So now I'm starting this kind of movie where you can basically go through the time series and you can see kind of what it did. You see that there's still motion going on. It doesn't look like salt, pepper, TV noise, right? So for example, now if I bring the fMRI without Nordic to the top, you see there's much more noise going on. And there's a bit of compression going on. I'm doing this online, but overall I think you get the idea that now the thermal noise component is significantly reduced. So let's close the online MATLAB now and see how the statistical activation map is different now. So I'm going further in my table of all the commands that we're going to execute and basically do the same thing, but as an input I'm not using the normal time series but the denoise time series. So I'm copying this and pasting it into my terminal. And it's finished, and we should have a new stat file now. Let's find it. Where is it? Maybe I go to my desktop here so I have all my files. Maybe I don't do that. I close this. There we do have it. Stats post Nordic. I need both of them open. So here I'm dragging, dropping it into my FSLIs. So now again I can select a threshold. So I don't want to see anything below 12, and maybe I go all the way up to 30. So now you can see a lot happened there. A lot of these kind of false positives are gone. It cleaned up a lot in the brain too. However, some of it is not cleaned, which seems to be then the true activity. This weird thing is still there to some degree. We have a lot of nice activity in dead sulcus. This is kind of more packed together. So we removed a lot of thermal noise components now. This means, however, that any kind of estimation of the residual might not make sense so much anymore. So for example, as soon as you do Nordic, you kind of reduce your degrees of freedom in statistical analysis. So I would only apply Nordic if you then do statistical analysis, for example, across participants or across sessions or something like that. Because now, we cannot really, it's hard to interpret the variance of the remaining signal. Let's try to clean it further. For example, we do know that there are some voxels that in the same patch of the cortex that are usually kind of clumped together, and very often we have specific hypotheses about layer fMRI that refer to the entire brain area and not only individual columns. In those cases where we can kind of sacrifice the columnar resolution, it makes sense to do layer smoothing. So let's do that. You can see here there is a layer smooth command from Laney. I'm copying this one and going back to my terminal to execute that now. So maybe a bit bigger because we have a long command here. So it's basically using the ln layer smooth command with the input file of the already denoised Nordic layer-fMRI, and I'm smoothing within the layers with a full width maximum of 0.7. If you're interested in what all those parameters do, we can, for example, use the -help option and then look at more. So here basically it tells you everything that it needs and how the full width maximum is estimated in units of millimeter and so on. You can also do it only within a mask, or basically only mask everything where we don't have a layer. The beauty of doing layer smooth, however, is that it usually suppresses any activity outside the brain anyway, because if the outside of the brain is basically considered as one layer, then this results in isotropic smoothing. So you have a lot of smoothing in all spatial directions, whereas within the layers you only have smoothing within the layer, right, in one spatial dimension. So basically layer smoothing is not only helpful to really clean up the signal within the brain, but also very often it is kind of an inherent brain mask filter too, which I think is one reason that I use it sometimes. So let's execute that now without help, and let's actually do it. And here we are applying the layer smooth on the entire time series. I'm not only applying it on the statistical activation map, but basically estimating my smoothing kernel once and then applying it to the entire time series. This is done now, and now we have a smoothed post-Nordic time series. Let's look at that. Right there, and I drag and drop it to the FSLIs. So now you can see a lot changed compared to the original one. Maybe I do the windowing in the same, from 0 to 30,000. And it's almost kind of comic-like, right? You see that it kind of looks nicer, but it also looks too good to be true. So you certainly have loss in spatial resolution, even though the edges of between the layers are still being preserved. So let's see how this helps our time series now, our time series analysis of the statistical activation. So now I'm copying the 3D deconvolve again. So we are again estimating the activation maps, now with the smoothed post-Nordic time series. And I'm copy pasting this command and hit enter. So now we should have another time series. And there we are. I drag and drop it into my FSLIs. And now want to look at it. Again, maybe for the statistics between 12 and 30. This is what we had done before. And you can see it cleaned up a bit more. It's kind of more patchy. This patch seems to be almost disappeared. Other patches seem to be kind of more consistent and might even increase the threshold that we're using there. There are still a few false positives out there, which wouldn't be too concerning. Maybe this is a bit concerning and annoying because we wouldn't expect activity here in the sagittal sinus. So let's apply the last step of cleaning your data. Namely, let's do a clustering threshold, which again is being done in AFNI. And here I'm using the 3D clust command. Basically, I'm using the statistical output that we just generated. I'm basically only using cluster sizes more than 35, and I have a size of like a distance for a cluster to be included is 0.9 millimeter at the threshold of 8, and then the output would be nice statistics of the post-Nordic smoothed time series. So I copy the entire thing and paste it there. And now I should have a file that's called nice statistics, which I'm gonna drag and drop in here. And again, I'm using the same statistical thresholds of 12 and 30,000, 12 and 30, excuse me. I'm making it red, and now I can basically remove this one, and you can see how nice and clean it is now. So we have some patches that seem to be clearly activated, some patches disappeared, and this looks kind of nice and clean, and convinces myself that we do have statistical activation, actually not only in this patch where it was kind of obvious before, but maybe also specifically in that patch. And in some of them, I'm still not sure if there's something going on at all. And with this, we are done with the second hands-on, and I thank you for your attention.